Okay, we got the study guide for Unit 1 here. Once again, I want to warn you all that not all the questions will be the same on the test, but this is a pretty good way to figure out what you know. We'll go through and talk about each one of these definitions. Remember, we try to work it so that the definitions are as short as possible. We'll start with the metric system. So, for the metric system, all I'm looking for is basically, a base 10 universal system of measurement. Um, we talk about a fundamental unit. All you need to know is what they are. They're the kilogram, the meter, and the second. And these are our building blocks for everything else. And a derived unit is two or more fundamental units. Um, Precision, you can go with uncertainty, one word definition, or if you like, you could say how close you are to the average. We talk about accuracy. We're talking about one word definition of error, or how close you are to true answer. Parallax is when you view something at an angle or take a measurement at an angle. So you view at an angle. Sig figs, those are the precise numbers of measurement. Precise number of measurement. Physics, I don't even know if I need to define that one, but I will. So physics is just simply the study of matter and energy. Linear equation, y equals mx plus b. Quadratic equation, or parabolic, is y equals ax squared plus bx plus c. And inverse is y equals a over x. So these are our definitions to start it off. Now the reason we do the definition section is so later if you have a question you can kind of at least know what they're asking for, because you'll know all the definitions for all the terms. Explain with examples a two-part definition for measurement. So here we go. A measurement first of all is, assigning numbers to objects. Also remember that it is going to tell us two things. So what two things does it tell us? Well, one, it tells us, what a number is not. So what a number isn't, and the second thing it tells us is what tool we used. If we take a look at what a number is not, it really comes down to rounding. Remember, you never really know what the right answer is because you can always pay some more money, get a better tool, and go further and further to the right. So when I say what a number is not, let's just take an example of a number. Let's say we had the number 12.3. Now we know for sure that it is not going to be any number that is less than 12.24, because if we round right there, it'll stay 12.2. And we also know on the other extreme that 12.35, if we round right there, that'd be 12.4. So anything greater than that or anything less than or equal to that, we know that it's not that, and we know that it's not that. However, it could be anything, really. I mean, I could fill up this entire paper with options of what it could be. So it could be infinity. Let me give you an example. I mean, it could be 12.32. That would work. It could be 12.29. That would be it as well. Now we can get kind of crazy and we could say, you know, it could be 12.315782131753. I mean, it could be that, and I could continue to come up with examples forever. So that's why we know what it's not. We know a range of what it's not, and we also know there is an infinite number of possibilities of what it could be. Let's talk about what tool we used. What tool we use, you know, it matters whether or not I'm using, like, let's say a double pan balance. With the double pan balance, as we used in class, we have these riders, and you put your sample over here, and then you know you can add mass over here, or you can adjust the riders. And as you adjust the riders, you come up with an answer that is good to the hundredth of a gram. Now in class, we also used a machine called an analytic balance that is located inside a glass box, and we read the number here. It's digital, it's exact, it goes 4 places to the right. So there's a great deal of difference in precision there. And if I saw a number like 1232 grams, I know that I used this tool. I know that I did not use the analytic. And somebody had to pay a lot of money to use these tools, and we got to give them credit. And that's why a measurement tells us 2 things. And one of those things is what tool we used. Okay, let's talk about the difference in the precision between meter sticks and calipers. This kind of goes along with what we were talking about. You know, if we look at some calipers, you can see that it's measured in millimeters, and we have a tenth of a millimeter mark. That means the caliper's got the smallest estimated number of the hundredth of a millimeter. If we take a look at a meter stick, and we look at the smallest graduation is a millimeter, and so a meter stick is only good to the tenth of a millimeter. So this would be our, you know, our calipers, and this would be our meter stick. So they're very different in how far they go. But it asks you to do it in centimeters. So if I was going to record a number with a meter stick, you know, I would turn it into a certain number of centimeters. I could go 2 places to the right, and with the calipers I could go 3 places to the right. And so that's how far you would take each of these numbers out. And we saw that in lab, and this is another example of precision, right? It matters what tool you use, and the number of places that you round to is dictated by the smallest mark on the tool, and you go 1 more. Let's take a look at some real life situations for each of the 3 relationships. So we have linear, we have quadratic, and we have inverse. These are our relationships. We can easily come up with some easy relationships. You know, we can do meters per second, and it shows us an object that's traveling at a constant speed. That's an easy one. And we could do other ones too. We could make it mass over volume and show density. You know, there are many different things you can do for a linear relationship. Quadratic, you can do meters and seconds again, and you can represent something called constant acceleration. So it's going faster and faster and faster at a regular rate. We'll give you that parabolic relationship. The key term there being it's x squared, where here it's x. Here we're looking at something that's 1 over x. That's called inverse. We look at inverse. One gets bigger, one gets smaller. We talked about trip time, so we could put, you know, velocity here and time here, seconds and meters per second, and we could end up explaining, you know, if we're going really fast, that would be up here. It doesn't take very long, but if we're going very slow, it takes very long, and that's a great relationship. Lastly, in the conceptual, looks like we're approaching 10 minutes here. So lastly, in the conceptual, we have the 3 fundamental quantities and units for physics. So the 3 fundamentals are the kilogram, the meter, and second. And what those are going to do is they're going to make up all the other 7 derived quantities that we're going to have in the first semester. So we have meters cubed, which is volume. We have meters squared, which is area. We have kilogram over meters cubed, which is density. We have kilogram times meter per second squared, which is force. And you can also measure that with the Newton. You have a kilogram times a meter per second, which is momentum. How many is that? 1, 2, 3, 4, 5. We have acceleration, which is meters per second squared. And we also have, meters per second, which is called typically by physics types velocity, but at this point I'd also accept speed. So those are our derived quantities and units created from the fundamentals.